Hi, if you've been paying attention to the news in astronomy, you may have seen something about one of the brightest stars in the sky, Fomalhaut. It has a debris disk, a beautiful disk of material that surrounds it. And as of yesterday, what were released are images taken by the James Webb Space Telescope of this disk of material. And many of the features and structures that are found in it are brand new discoveries, some of which very strongly suggest unseen planets. So it is a stellar system that you can see relatively directly with the James Webb Telescope imagery. And I am so fortunate to have been given the opportunity to work with that data as part of a press release. So I had a chance to work with some astronomers at Stewart Observatory here at the University of Arizona. A famous astronomer named Dr. George Ricci, and another astronomer that's been working on this project named Dr. Andras Gaspar. And the two of them invited me to come in and, as part of the press release, develop different versions of this data, kind of process the image in the way that an astrophotographer would, and then perhaps be part of the press release to make it a compelling image. So what I'd like to do in this video is show you a little bit of my experience. I'd like to tell the story of the science as well as tell you my story of being able to work with this data. It is just quite an exceptional opportunity to be able to work with data, especially that no one has yet seen. I mean, it's just really, really cool. So I've been waiting for this opportunity to show off some of the images that I had a chance to work on. The Space Science Institute, they made their own version of their press release, but separately, Stewart Observatory and some of the images that I made also generated some information as part of a press release. And so I'd like to give you a little bit of the behind the scenes of what the data actually look like. So come on, let's go and check it out. So let's begin with a quick introduction to Fomalhaut. It is one of the brighter stars in the night sky, and it's relatively close to us at around 25 light years away. It's a multiple star system. It has a couple of companions, and it is a star that's a bit brighter, hotter, and a little bit larger than our own sun, and that's going to affect the environment that surrounds the star. Now, to be able to observe anything that is surrounding Fomalhaut is a big, big challenge, because Fomalhaut is so bright, at least in the visible wavelengths of light. It's just so bright that in order to see anything, you have to block the light of the star. So for example, the Hubble Space Telescope observed this star, and they used an instrument that has a coronagraph that literally eclipses or blocks the light of Fomalhaut to try to be able to detect the stuff that is surrounding it. Let me show you what an image of that looks like. It looks like this. This is not the complete image. I'll show you a more complete one in a moment. But most of the information that you see here is actually an artifact of, or an effect, if you will, instrumental effect of the diffraction of light around the coronagraph. So Fomalhaut is right here in the middle, and then you get all this diffracted, scattered light. But the ring that we see here, and it's easy to see. I mean, our eyes and brains can easily see that, even though we have this other thing going on. And so as a scientific image, this is pure gold. I mean, this is the kind of thing that discoveries are made of. But as an astrophotograph, when I look at this, just setting aside how amazing the science is and how challenging and difficult it is to take a picture like this, it's not a great astrophotograph, not by the standards that astrophotographers go after, because we're just interested in much brighter signal compared to all of the other problems that an image might have. Here, the kind of things that we're not interested in are at the same level as the stuff that we are interested in. So this is, be it as it may, this is what an image from HST looks like. Let me then show you another kind of way to observe it. If you observe, instead of observing this scattered light from the particles here that are orbiting Fomalhaut, because it's just a very, very tiny amount of light. It's very difficult. But at longer wavelengths of light, the material that is surrounding the star can re-radiate at other wavelengths of light, like in the infrared wavelengths, which is what JWST observes at, and even longer wavelengths than that, sub-millimeter wavelengths of light. So let me show you an example of what an image like that looks like. So this is ALMA data, and this is sub-millimeter wavelengths of light. Again, you can see Fomalhaut, the impression of it here in the middle, and you can see the ring. And this is the same ring as what we're seeing here. Now, there are different scales and the different orientations and all of that, but ignore that for just a moment. Here, though, we can see that it has this material that is obviously re-radiating light. But there is more to be seen in the system. This information that I'm showing right here was basically all that was known for many, many years. So it's known that Fomalhaut has this disk of material. It has at least a major ring of material, but that already hints at that can't be all that there is. There must be more to it. There must be a disk. There's something that makes this ring of material. So we get to an image that looks like this, and indeed, the science really, really was amazing with this image. So this is now, we're looking at the complete ring, the artifacts kind of look like the eye of Sauron, if you're into that kind of iconography here. And within the ring, they found something that over the years changed in its position, but it also changed in its brightness. Originally, it was thought to be, because it was orbiting, seemingly moving, it was thought to be a potential exoplanet, a planet right there in direct imaging to be seen. But as what is modeled here, and this work was done by Andras, Dr. Gaspar, to show that this not a planet at all, but instead it is a huge cloud of dust. Probably what happens, the thing that forms the ring and the thing that happens in these disks of material is stuff runs into one another. And when that happens, you get perhaps smaller particles being generated. So if you had an asteroid, two asteroids that come together, they may smash together and make a big cloud of dust. And that could very well be what this was. As it changed through time, it was initially bright, but then became faded until it just couldn't be seen anymore. But that dynamical process of things coming together, colliding and mixing, is an important one because it's something that maintains a debris disk that surrounds a star like Fomalhaut. And the thing to kind of keep in mind is the picture, when we see this information, this picture is a picture that is a reflection perhaps of our own history. When we consider what happened in our own solar system, we have very similar structures, and I'll be pointing those out. In the picture, we have the same structures or analogs of them within our own solar system. So now let me show what happens when you have multiple kinds of information. So we have, this information from HST, and then we had the ALMA information, right? Which was this crazy ring, which I love. I mean, it just looks so beautiful. Notice how it is offset, seemingly, from Fomalhaut. That also hints at, again, the dynamics, the kinematics of the system. Maybe that there is something else that we're not seeing here, another mass that could be affecting the overall orbits of particles within the system. But we can see at an image like this how someone, and this is now coming back to the kind of thing that I was trying to do with the JWST data, someone put together this version of the image which tries to blend the two. You want to show that these are they're the same rings. We're getting the emission or scattering of light in that same part of the disk. And so how do you do that? How do you combine these two disparate images together in some reasonable way? Well, this was the idea that someone had, where you can see kind of half is HST and then the other half overlaid is the ALMA data, right? I had the same conundrum in how to try to blend together multiple sets of data in a similar way, and I'll be showing you that in just a moment. But here's the thing about images like this. There's always a danger in the interpretation of the image. Something can look great, but easily be misinterpreted. For example, look at an image like this. So this image, I mean, it looks cool, I guess, but it maybe is not as informative as the other image. So you can judge for yourself. Here we have an overlay where they put the entire ring from ALMA over the HST image, which is what they said in the article. But the problem here is that you're not actually seeing the ring, the actual data, the interesting part. of the HST data. This is just the scattered diffracted light, the effect of the coronagraph. That's all we're seeing here. So it's serving only to look cool, maybe, as a graphical thing, but it isn't really the HST data, and so I think that might be a little misleading. But it does look cool. So I definitely wanted to avoid that in the image or images that I was going to work to create. So now let's just look at some of the data and you can kind of see what things look like. Another interesting element to what I'm doing here is that I'm also a PixInsight ambassador. And here I used PixInsight to do some of the processing as part of the creation of these images that were going to be part of the press release. What a wonderful connection to be able to do that kind of thing, to be an ambassador for this kind of software where I obviously create videos that explain how to use it, and I actually use it on some of the coolest data you can get your hands on. So with that in mind, let's just look at the HST image here. This is what an HST image looks like just from the beginning. The values, the difference between what is kind of not interesting, what is interesting here, is tiny, tiny, tiny. So you have to really, really stretch the image. I'm going to show you the version of the image here that is unstretched, and then just watch what I have to do in order to be able to see anything at all. I have to get these little carrots very, very close together. And then you can start to see that there's information showing up here in a very, very small range of brightness values. So we'll make it a little bit larger so you can see what's going on. But this is what that data actually looks like. Here we go. Go like this. Zoom in. Go like that. Keep stretching it. And what is really cool about this particular version of the image, or the data, is that this has been worked on by Dr. Gaspar. He tried to minimize some of the this radial pattern that you have, the artifacts, I'll call it instrumental artifacts that you get in the HST data. Now this data took an extraordinary effort to generate, and then he went yet more steps to try to improve it by trying to minimize that effect. It makes the ring stand out a little bit more, make it a little bit easier. And that, of course, helps me in what I needed to do, which is to try to, in some way, extract this ring so that I could use it as a composite image, which I'll be showing you. That is one of the goals, was to try to create a composite image that showed not only the JWST data, but to overlay these other data, the HST and the ALMA data, all together, because that tells another very interesting story. The JWST data in and of itself is amazing, and then when you overlay these other observations, it tells even more of the story. Now here's what the ALMA data looks like. It's this beautiful ring. You'll notice, of course, that these images don't have a color assigned to them. Now they were taken with a particular filter, for example, the HST data here, taken through a particular filter at a particular wavelength, but not yet colored in the sense that we're going to choose a color mapping, especially if we're going to try to combine this information to tell a particular story. So we just have grayscale images initially here that we're going to be working with. And finally, let's look at, of course, the JWST data, which is here. So this is what it looks like kind of before you do anything to it. In terms of stretching the information, again, we have to go through that process. It looks like there's nothing there, but there is something there, and it's really, really cool. So like HST, we do have an obstruction here that blocks out the majority of the light from Fomalhaut, but this wavelength of light, this is infrared or mid-infrared, because this is the MIRI instrument, which is the mid-infrared instrumentation. And let's make the image a bit brighter, a bit more contrast. And now you can start to see the interesting stuff. So in and of itself, at this point, we now can see just that same ring. This is the same ring that we're basically seeing in the ALMA data, that we're seeing in the HST data. Here it is with JWST, but there's more. And that is what makes this interesting. Because if we continue to increase the contrast, you can start to see all kinds of cool stuff. I just can't imagine what the astronomers, when they first saw this, I mean, it's just amazing. Because not only do we see the ring, but you start to see, of course, there's an inner gap, there's an inner ring, there is a halo. There's stuff that goes outside of this ring. In fact, if you continue to brighten this to a certain level, you can really see that the disk is quite full in terms of in emission, from an emission sense. There really is quite a bit of information. The total exposure time here, for all of the exposures that were taken, it's less than an hour. It's like a little more than half an hour's worth of time. What if they spent, right? What if they spent 10 hours on this kind of thing? Imagine what this disk would look like, how far it might extend outward, and perhaps some of the signal would be inside the disk to see some of the variations. Amazing. But as it is, this is what the data looks like. So just a couple of other notes here. You will see that there are some other dots in the frame, some of which are probably background stars, something like this, and some of these things are, or they could be background galaxies. And you'll notice that there's a little thing right here that is seemingly superimposed on, if it's not within, the ring. Almost looks like a little star, right? And that very well could be a star, or it could be another one of those clouds of dust. So I'll get back to that in just a moment. So there's one more image that I want to show you, and it turns out that as far as an astrophotograph, it's very useful. There is more data that was taken at a different wavelength of light of the very center. It shows the very center of here this disk of material. At this wavelength of light, you don't see the rest of the disk. We're just looking at what is the very heart here. And what's nice about that is that this data then can be useful to kind of fill in that hole, because that hole is, objectionable at some level. Now, for science purposes, we don't want to mess with it, but for purposes of kind of demonstrating the fullness of the information that we can tell this story, it's nice to have other data that we might be able to substitute in there. Although this data, as you can see, in and of itself is a little wonky. So I'll tell you about that in just a moment. One of the reasons that this observation is important is that it is not completely spherical, and at some level, geometric sense, that tells you something about this inner disk. Now, the hard part here would seem to be aligning all of this stuff, because now we have 4 images. We have this kind of central information, we have the JWST data, we have this HST data, and we also have the ALMA data. And they're very different images, different scales, different potentially rotations, and all of that. So what I did is, and this is where PixInsight is nice, what I did is I took what comes with this data, or some of it, were the astrometric solutions. And one of the things is that you can align by coordinates in PixInsight. So that helps to do the alignment, because I can't do a star registration here, but I can align based on the coordinates. And in that way, because there was an astrometric solution associated with each of these frames, I could, with some good fidelity, know that the registration was good. And that is important to tell another interesting part of the story that I'll get to in just a second. Going back to the original JWST image, let me just show you some of the steps that I performed that I think really worked towards the final result that I was looking to get. Here's the linear image, and of course, taking a step forward, I had to choose some level of stretch. Now, this is a very typical kind of stretch in the sense that it's like that exponential logarithmic stretch that shows as much of the information as you can, but it'll also show, in this case, the center very bright. And these features don't really stand out in terms of the ultimate contrast that we'd like to perhaps achieve. So the next kind of step that I did is to employ a kind of deconvolution here. And so this deconvolution certainly sharpened the stars. The disk itself doesn't get that much more distinct, though some of the low contrast features stand out just a little bit more. So let me show you that again. This is before and after. But perhaps what I think is the most important, or certainly the one that has the biggest effect, the process of HDRMT in PixInsight. This is the high dynamic range multiscale transformation that's going to take this brightness of the center and bring it down. It's going to equalize these brightnesses a bit at a particular scale, and that's what makes it so interesting. And in doing so, let me go forward here. Now some of these inner features I feel can be enhanced further with more contrast adjustments, because now we can really see them. You can almost see how the ring wants to complete here against this backside. Comes around the front, the gap, and then you can almost see some features here where it continues to go further. So increasing that contrast would help to some degree. Keep in mind that the entire disk is only 10 to 15 or so arc seconds in extent. So these are very, very small features. But it's this adjustment with HDRMT that I think really gave me some purchase to be able to move forward and do some of the other things that I wanted to do. Let's turn our attention to the science and the discoveries that this image shows us. This data was originally processed by Dr. Gashpar, and later further processing was done by people at the Space Science Institute, and they created this graphic, which now you can see published everywhere on the internet. And this image offers a lot of information about the system. One of the interesting things, though, I think, is what this image, the story that this image tells us, is a story not only about Fomalhaut, but it's also a story about us, in the sense that here we are looking at a star that has a stellar system of material surrounding it, which includes perhaps dust, small bodies, perhaps asteroids, and very likely unseen planets, perhaps to be discovered soon, directly discovered soon. Well, that's the kind of place that we live in. We live in a solar system of stuff. We live in a solar system that has planets, asteroids, and dust. When we look at an image like this, we are looking at the material that is being warmed by Fomalhaut, by this central star, and then it is emitting wavelengths of light that come to us in the infrared, such that JWST can see it, and we get a wonderful, I would even claim, an exquisite image like this. Because this system is so close to us, we can see it in just wonderful detail. Now you might think to ourselves, well, the place that we live, our solar system looks nothing like this. But it actually does. And you can even see this for yourself if you go outside on a moonless night away from the city. One of the things that you can see in the night sky is something called zodiacal light. And this is light scattered by the sun, sun-scattered light, from dust that is within the plane of our solar system. So if there was a JWST telescope over there at Fomalhaut looking back at us, it would be possible to see a glowing disk surrounding our sun. And there would perhaps even be gaps or rings, because perhaps, our asteroids or something like that would also be emitting some of this light. Though our solar system is perhaps more rarefied than this one is, one of the things that makes the Fomalhaut system interesting is that these rings and some of these structures are distinct, which means that there's probably a lot of dynamics taking place here, where things might be colliding with one another and producing dust and producing these particles that are being warmed by the star. Another analogy to our own solar system, as demonstrated here in this image, is the major ring, the outermost ring. It's the one that was originally discovered both with the HST data and also the ALMA data. Shown here, it's this outermost ring, labeled here KBA. That is the Kuiper Belt analog. And it's called that because it harkens to the fact that we too, our solar system, has a Kuiper Belt. The Kuiper Belt are those bodies, small bodies, that live beyond, say, the orbit of Neptune. And Neptune is about between 30 to 40 or so astronomical Earth-Sun distances away. That's where the Kuiper Belt in our solar system begins. And no one really knows exactly how far it extends, but it goes for many more astronomical units away. Here, this system is a little bit larger in scale because of the nature of the star itself, such that this distance, perhaps from Fomalhaut all the way to the ring, is about twice that of what it is in our own solar system. Perhaps this is on the order of 80 astronomical units. One of the interesting kinds of dynamics in solar systems such as our own is that as the planets orbit the sun, they affect the environment that is surrounding them. They are in perhaps resonance with, gravitationally speaking, in resonance with the other things that are orbiting the sun. And that can cause the gravitational effects of these planets to push and pull on things and generate either enhancements or voids in a disk of material. That's one of the reasons why in an image like this, when we see this inner structure, this inner ring, the kind of thing that would very likely make a structure like that is something that would be, again, pushing or pulling particles to generate an enhancement or a gap. And so that's why there is this strong evidence for unseen planets in a system like this. We, in our own solar system, this same effect takes place. Our asteroid belt between the orbits of Mars and Jupiter, Jupiter having the biggest effect, throws things out of the solar system, or it corrals some of the objects that are, say, closer to the sun, and we have a very well-defined asteroid belt between, say, Mars and Jupiter, and then again a scattered disk well beyond that begins perhaps with the Kuiper belt and then goes well beyond, where all kinds of other things have been thrown out of the solar system in like a spherical halo-like distribution. That's perhaps where all the comets reside. So this system isn't so much a system that is currently forming planets. It's very likely that everything that is formed has already done so here. But it's still a dynamic place where a dust cloud, and you can see here that it's a little bit hard to see, at least as the astrophotographer in me would say, that's something that we would want to enhance in our final image, as well as some of these other features. But if this is truly a great dust cloud, it must have been caused by something, and very likely it would be the collision of something within the ring. So the story really is that by learning about this Fomalhaut system, we learn an awful lot about ourselves. And then you can ask questions like, is this a typical thing? Is it typical to have an asteroid belt or other features close to the sun? Lots of dust close to the sun, that is true in our system. It's also true here, but perhaps even more so here in the Fomalhaut system. Or have these Kuiper belt objects, is that a typical thing of another stellar system? So those are the big questions, but they can potentially be answered by observations exactly like this. That's the story that an image like this really tells. So of course I wanted to tell that story too. And as you recall, I wanted to enhance more of these structures, bring more contrast to them. So now let me show you my view, that is just the view of the JWST data, although it has a little enhancement here. That is this one right here. And with this image, I obviously just chose a more yellow color. The color doesn't matter at all. It's totally arbitrary. I just like the lightness of it. But a much brighter image, but brighter only in the sense that the halo is shown much more. That is everything that is beyond the ring. Here it looks like, the ring just kind of abruptly ends, but if you look at the data, it's obvious that there is more in the halo than is being shown here. It doesn't mean you have to show it, but I wanted to tell that story. There is a little bit more there. If they could take even longer exposures, I think that that would show up even better. So now you can see how this ring is an enhancement within this disk, and of course there's also an inner ring, and that inner ring has its own gap. So with these additional contrast enhancements, we can, as an astrophotographer, we like to bring that those features to their nth degree that's possible within the data, right? And I think that this kind of goes towards that story. Because of the deconvolution, the great dust cloud here also shows up a little bit better. And you also, always want to tell a story that doesn't have something that is distracting. This is often the case in many astronomical images. It could be bright stars, it could be certain kinds of artifacts, like the HST data. Here, it would be that central obstruction. That's just the nature of the kind of blocking of light that's necessary. But if we substitute another bit of data from another filter in its place, and it is of that same region, then we get kind of a more holistic, I think, result. Now, just producing this image was only part of the assignment. The reason that I was brought on the team was really to generate this and composite the other data as well, because it tells yet more of the story by overlaying the ALMA and the HST data on the JWST data here, that you can tell even more of the story of what's going on in this system. So let me just point out the fact that when I began with the HST data, obviously I just tried to crop out, the majority of the stuff, and then do what I could to minimize all of that noisy stuff. But this is kind of where I began. It was with a section of the HST that was scaled down to the same size as the other image. And then, by using some tricks, try to just remove by some threshold everything that is not really relevant or of interest, just the major signal that HST was basically providing. And that's kind of what you're getting here, is this HST kind of ring of data. Now this still needs to be blended even more. One of the blending techniques that you can employ in Photoshop is something called blend if, and you can specify the condition either by color or by tonal value as to how one image is blended with another, and that was critical for getting something that looks kind of reasonable. So here is what the actual composite looks like, but I can kind of disassemble this composite for you and show you what the different layers look like. So I'm going to turn off the HST layer just so you can see how well the ALMA data, and this is the even redder data, if you will, it has a lower resolution than either obviously the HST or the JWST data. So it has kind of this bumpy ring-like structure to it, but it basically overlays right on the top of that outermost Kuiper Belt analog ring. This also demonstrates something else. You can see that these two rings are not quite I don't know whether they're elliptical. They're not concentric, and that in and of itself is also a very interesting observation. I will tell you that getting these kinds of things to blend very well with one another was really a challenge, but at the end of the day, was able to get it to, I think, look somewhat good. Here's the central region, and you can see that I just literally erased everything here in the middle, leaving room to put this kind of central bit. Now the central bit that you see there, that was taken through a different filter, the 1550 filter here, and it had all of this all of these artifacts. So what did I do is I used in Photoshop, there's something called a surface blur, and I went ahead and I applied a surface blur to that data, colored it a slightly different color, and then put it, it's registered again by coordinates, so put it right there in the center. And that's how I ended up with that particular aspect. It looks like there's a little star in there. It's not actually Fomalhaut. In fact, there was some discussion about, literally putting the PSF of Fomalhaut right in the middle to indicate that's where it is. But it looked kind of weird, so we decided against it. And I think that was the right decision. It just looked very odd. And then finally, what I find the most fascinating is the HST data, because when you overlay the HST data, now I actually put the ALMA image, you can see that that group is above, the ALMA stuff is above the HST, so when you overlay it, you can see that the HST peeks out from underneath, if you will, the ALMA data, and therefore goes beyond that KBA ring, the large ring, the Kuiper Belt ring. And that signifies something interesting. HST observes in the visual wavelengths of light. That means that the particles that are being observed are not glowing in the infrared wavelengths of light, not re-radiating their photons. They are literally scattering or reflecting light from Fomalhaut. And that only happens at certain angles, so you're not seeing all of the dust there. But of that dust, those particles are going to be very small particles, just because the wavelengths of light, visible wavelengths of light, are much shorter. And so they are scattered, but that's indicating that the particles are very, very small. And the thing about small particles is that they are more easily influenced by the stellar wind of Fomalhaut. meaning that winds from the star, our own sun has a solar wind, but winds from Fomalhaut blow smaller particles radially away from the star more easily than the more massive stuff. And so there is this differentiation in mass by virtue of the stellar wind. So the ring of dust that HST sees are smaller particles, and so the ring is broader, and that's why we see it peeking out here. And I think that that is just fascinating, that you can infer all of that physics and those dynamics just from the fact that when we overlay these images, one is a little bit broader than the other. Now, at the end of the day, when I gave the astronomers the final version of the composite here, I ended up giving them this one, which is a little more yellow, but I just liked it. I felt it was happier. It's a little bit brighter, and I thought it just kind of blended better and would be more appealing to the eye if you were to see this, when it's published as a press release. It initially might be pretty small and just so catch your eye with a little more ease. One of the interesting lessons I learned is that because this image, the composite image, became available, but in this form, I fear that it fell into the trap, like so many other images can, where there's a misinterpretation as to what this image actually is. People were describing the discoveries, describing asteroid belts and so on, and the fear, I think I saw the reality of, is that it was interpreted that these rings, these other observations from ALMA and HST, that's the asteroid belt or something, and it's not that. This is a composite of these different observations, and they give you a very deep story about what's going on. If I had to do it again, I would have never made the image in this form available. I think that it probably would be best to make it in a form where it is really explained quite literally with labels and broken apart so that you can really see what I did, which is to put these images all sandwiched together, but still give you that general story of what's going on. So that's basically the story that I wanted to tell. I include in the link down below a link to my website that has these images so you can look at them in some more detail and check them out. But right at the top of the page, you'll also see there is a link to the paper that the astronomers, Dr. Ricci and Dr. Gaspar, wrote about these discoveries, about this image. And it's actually quite readable. Sometimes these papers are pretty dense. This one you can actually read and understand a great deal of it. There's also a press release by the University of Arizona and another one, of course, by STSCI. So check out all of this information. Let me know what you thought of the discovery of these images, of my way of thinking about communicating the excitement and the discoveries of the data, and so on. Thanks a lot for joining me, and I hope you enjoyed this kind of a little bit of a deep dive into what will now become a thing to look at, perhaps to find planets soon orbiting Fomalhaut. That would be amazing.